Jai Hind everyone. My name is Gunjan Saxena, Assistant Professor Ajay Kumar Garg, Engineering College. So today I am here in the continuing the series of DA. Today I am taking a topic from Unit 4, which is single source shortest path and its approaches. Basically, in this particular topic, what we are doing, what we are suggesting, suppose we have a point A and we have point B, C, D, E, F, G and so on. What you want. So, what is the target? Target is we want to go from A to B, A to C, A to D and so on. And we want the minimum cost, or we can say a minimum time taking from A to all over the point. So, this is called as single source shortest path. That means there are so many vertices are there and one source is there. Suppose we are residing at Akgec college and we want to move ABS, we want to move kite, we want to move IMS and we want to move RKGIT. Then what would be the best part? We have to choose from Akg for consuming or capturing all these particular colleges by using minimum cost, or we can say minimum time. So, let's start. So, first of all, we need to know what is single source shortest path. In single source shortest path, there is a set of graph, as we say, the graph G, and this particular graph G having number of vertices and number of edges. We can say the V vertices and E edges. We have weighted graph. So, what we are saying, the graph should be weighted. For example, if we are traveling from Akg to kite, or we can say Akg to IMS, then some parameter should be there to consider which path is better. Maybe we are taking a cost, or we can say maybe we are taking a time. What is the time is taking from Akg to IMS by choosing this road? What particular path we need to take if we are going one point to another point. So, the next point is the edges in G have a weight. As we discuss, every edge having a different weight. In this particular example, as we are taking two different colleges and we are moving from one college to another college, that means the weight in this particular example is just like a time. What time is required from A point to B point, and suppose we are going to take another path by using a C or by using a D, which having a minimum cost, we are just taking that particular path. Just remember, not necessary always a direct path having a shortest weight, or we can say a shorter timing. Maybe in between node having make the the weight is minimal rather than direct path. Can be a directed and undirected, both type of graph we are having. Suppose the direction is there, so obviously we can follow that particular direction, and if we are having a graph which is no direction given, then we can move any of the direction. Okay, can be a connected or also be a disconnected. Let S be a specific vertex, or we can say a source vertex. For each vertex V, from all the vertices, what is the target of this particular single source shortest path? For each vertex V, compute the length of shortest path from S to V. What we are saying, if we are having some vertices, suppose this is A, this is B, this is S and this is C. So, example is saying just take a specific vertex, or we can say a special vertex called as S. Now, we need to compute a length of shortest path from S to different kind of vertices. Okay, this is the main target, or we can say this is the main definition actually. So, what is the example, or we can say by using this particular diagram, I am just try to said what is single source shortest path. So, let's consider this particular graph. In this graph, we are saying this S is a special node, or we can say told as a source node what we need to do, we want a particular shortest distance by using this particular S to all about the vertices given in this particular diagram. So what is the way, what is the so suppose we are here and when we need to go this particular node. So what is the weight? What is the distance between this particular vertex and this particular vertex, which is the weight of this particular edge, which is S. Okay. So what is the answer of this particular step? We said from V starting 0, obviously when we are standing upon standing at the AKG and we are start moving to another college, then the starting time of our travel is 0 initial. So at the place of S there is a discovery time which is 0, and the distance between this particular node and this particular node is 4. Then how much time we are taking to traveling this particular S to this node, which is 4. Okay. So in next particular slide we are just discussing about a very important property. The name is relax property. By using this relax property, we directly understood how this particular value become 4, how this particular value become 8, how this particular value becomes 12. So by using this particular relax property, we can examine, or we can say, we can check how we can calculate the relaxive situation or condition or particular vertices. Okay. So in the relax technique, a common operation that is used in the algorithm is called as relax operation. Okay, what was that? When a vertex V can be reached from the source with a certain distance, we examine an outgoing edge, say V comma W, and check if we can improve W. Can we improve this? How? Basically, this is the formula. Listen, this is the value what we are having. This is the value what we are wants, and this is the weight between these particular edges. Okay, so what we are saying, this S is initially 0. Believe me, we are standing at one point and we are just moving. We are just start moving. And what we are saying, the discovery time, or we can say the starting point of this particular S is 0 at the beginning. Now we are taking this particular edge, then what would be the weight for this particular vertex? Okay, then by using this formula, and one more thing we want to add, actually how this particular work is arises, or how this relax can be done. Suppose we are standing at this particular point and we have this node, we have this node, this, we are 5 nodes, or we can say 5 colleges we have to cover. But in the beginning, in the initial, we don't know what would be the time is covering from this particular S to this particular V. Are you getting? I am not knowing what is the value of this particular V when we are moving from S, what particular value of this particular node when we are moving from this. Then initially what we are thinking, what we are planning, the source node becomes 0 and all other vertices except source node assume to be like a infinity. Why infinity? As we don't know at the beginning what is the time when this particular vertex is going to be discovered. This is the main agenda, this is the main phenomena. Then now just put it these value in this particular formula. Na? What is W here? In this particular formula, by using this particular formula, this is W and this is V. Then what is the value? How we calculating this particular dW? So what they said if dW, that is infinite, is greater than dv, discovery time of v, that means this particular value which is 0 plus and weight of this particular age which is 4. Now what is said, infinity is greater than 4, which is exactly true. Okay, now what we can do, if this satisfied, then this particular value which is 4 is the value of this particular dw. Okay, now I believe you getting this point, how this particular 4 comes. Then what about this particular question mark? Again, this v, or we can say this s, having again the value of 0, and this particular node, suppose this is the x. Suppose this is the x node, then what is the discovery time of x? Initially, which is infinite, and infinite is greater than is what? ds, which is 0. And the weight between these particular two vertices is 8. And again, infinite is again greater than 8. Then what would be the value of dw, or we can say dx, which is 8. So this is the way how can we relax these particular node in the single source shortest path. Now let's move to the two approaches of this particular approach. The name is single source shortest path. There are two algorithms, there are two vertices, there are two technologies, or we can say approaches for finding the single source shortest path from any specific source. Then the first one is Dijkstra algorithm and another one is Wellman-Ford algorithm. In today's lecture, we are just taking the one approach, the name is Dijkstra algorithm. So there are some slight differences between Dijkstra and Wellman-Ford. In particular algorithm of Wellman-Ford, we can say if some negative weight are there, then Wellman-Ford can easily be tracked. But in Dijkstra, in case of Dijkstra, if some negative values are there, then maybe Dijkstra gives some vice result. Okay, so in short, we can say Dijkstra is most preferable when all the weight in particular graph, or we can say the value of age, should be positive. Okay, now what is Dijkstra? How Dijkstra works? Basically, for each vertices, initially, as we know a graph and we assumed, or we can say we know about the source vertex from where we are doing to start our shortest path process, So for each v, mark v as unvisited and set dv equals to infinite. As I said earlier, what we are saying when we are using Dijkstra and we are supposing, ds, which is the initial value, or we can say which is the source value, which to be equal to 0. Why so? As I said earlier, we are starting from this particular point and the beginning time at the initial state, which should be 0. Okay, and this particular dv, as we know, all the vertices, or we can say all the v from this particular v is now unvisited, and we don't know about what is the time, exactly time when this particular vertex should be reached. Okay, now v is unvisited vertex with the smallest d, and we visit and relax all its outgoing edges. What we are doing, we are just connecting, we are just edging all unvisited vertex with the smallest distance d, and just relax all the edges which is moving forward and which are going through the v. Okay. Now, this is the example. By using this particular example, we just see how the Dijkstra algorithm works, and for the university point of view, this particular example and this particular topic in theory is very, very important. Okay. Now, suppose this is the question we have and we just apply the Dijkstra algorithm in this particular graph. What we are doing, we are just doing the initial value, which is the source, the name as S, from 0, and all the vertices from V other than S, which is the source vertex, becomes infinite. And I tell you why we are doing so. Then now just relax these particular vertex as we said earlier, as we discussed in previous series or slide, what will be the value of this particular node, which is suppose this is the infinite, which is greater than 0 plus 4. Obviously this condition is true. Then what we are doing, the value of this particular node becomes 4 in place of infinite. And what about this particular vertex? Similarly, infinite is greater than 0 plus 8. Again, this particular 8 is always or we can say obviously smaller than this particular infinite. Then what we are doing, we are just changing this particular value infinite to 8. Okay, now this is the example, or we can say this is the diagram, what they are moving, what they are showing when we are choosing this particular 0, then this 0 to 4, how this particular infinite is to be replaced by 4. Okay, now in this particular next graph, what they are showing, when the source value is 0 and the discovery value is again infinite, then just relax these particular vertex and the infinite value should be replaced by this particular 8. Now, what we have to do, what we going through in the next, we are at 8. You maybe start from this particular 4. You can just relax this particular node also, no matter what kind of way, what path you are taking first. We just need to relax each and every vertices, each and every edges, and just picking the shortest value from one particular node to another node. Now, in this particular way, the listen, now in this particular situation, this is the S and this infinite should be just like a W. Okay, and what we are finding, we finding this particular dW, which is infinite, and the value, just comparing. What type of comparison? Comparison is, this is the weight value, which is 1, and now the source value, which is 8. So don't be confused. The source value is now this particular age is 8, not a 0. Okay, because this particular path we have already covered. We taking 8 minutes, or we can say we are just traveling 8 kilometer and just do this particular distance, and the value of this particular node become 8. Okay, then now what is the value of this particular W, which is 1 plus 8, which is 9, and obviously infinite is greater than 9. Okay, then what next? This particular infinite is replaced by 9, right? Similarly, this particular infinite, how this converted to 12? What is the way? The way is naturally this particular 8 plus 12, which is equals to 12, and this infinite is just replaced by this particular 12. Okay, now what about this infinite? What is the way how this particular thing is changed? You know, this is 8 and the weight of this particular age having 7, then 8 plus 7, which is 15. Obviously 15 is less than infinite. Just move, or we can say just remove this particular infinite by using this particular value. Okay, next. So this is the again next go through how this particular infinite converted into 11. Just check it. So this, the source value is 9 and the weight value, which is 2, and again 9 plus 2, which is 11, and this is really less than value to the infinite. Just replace this particular infinite to 11. So this is the go through. Now, what was the next? We are just look away. In previous slide, this is 15, and now in this particular slide, this is 14. What is the way? Why? How we can do so? Think. Suppose we are catching this particular way, this to this, this to this, we are having a weight 15. But if we are taking the way 0 to 8, 8 to 9, and 9 to this particular weight, then what would be the final weight? Just throw it. This is 9, suppose this is the S, and again this is our W, which value is 15 in this particular algorithm. Just see, this is S, this is W. What we are doing, DS, 9 is greater than, which is 9, sorry, this 15 is greater than 9 plus 6, which was what? Which was 15, which is not true. Okay, then what we are doing? We are just doing 9 plus 6, which is 8 plus 6, which is 40. Okay, next. So we are just moving through this particular 19. How we are getting this particular 19? We are just watching. If we are taking this 11 and 11 plus 14, this value is obviously very huge. What we are doing? We are just taking this particular path. This is 12 and this is 7. 12 plus 7, which is 9. By using this path, the value of this particular node is 19. And what about this 21? We are just taking 9 plus 9, which is 21. If we are taking if we are taking this particular path, which becomes a 28, so what kind of path we are taking? We are just taking 10 plus 11. So this is the final path, or we can say this is the final overlook about the Dijkstra algorithm. So at the beginning, at the end of this particular series, I just want to sum up of today's lecture. In today's lecture, basically, we are just thinking, or we are talking about a single source shortest path problem. What was that? If we are just want to move from one point to another point, we are just relaxing our particular vertices, or we can say or particular edges, to just getting the value of one point to another point in terms of maybe time or maybe in terms of weight, which is known as single source shortest path. And in this single source shortest path, we are just using an attribute which name is relax, and in this relax property, what we are doing, we are just relaxing all the vertices by using a particular formula or by using the particular process. And in this particular process, what we are saying, we are just assuming from the beginning of the go at the source value, which is obviously 0, and the another points, or we can say or the another vertices which are not discovered yet, then it will becomes infinite, because we don't know about the discovery time of these particular vertices. Just using this particular formula, we are just getting the relaxed value of each and every vertices. Okay, so in this lecture, this is all about. In the next lecture, maybe I am just making the another approach. The name is Wellman Ford. So Jai Hind everyone. Okay, thank you.